Hello, my name is Fatima Riakhi, and this presentation is about PV sizing of a standalone solar carpet system linked to charging stations and its economic analysis. This research is carried out within the scope of the Africa-Europe Bioclimatic Collaboration for the 21st Century project. The outline of the presentation includes a background about the Moroccan energy sector, photovoltaic solar carpet, methodology and results, the amount of mitigated CO2, and the conclusion. The Moroccan energy sector known high energy import bills for fossil fuels and the yearly electricity demand expected to exceed 6.5% from 2015 to 2030. Therefore, the national aim is to increase electricity generation from renewable sources. The shift toward clean energy generation is encouraged by the installation of solar carpets, which are ground-mounted structures with a slightly tilted roof by 10 degrees. They come in three types, but the optimal type is the monopitch. Why we would think about this solution? Because many parking lots are taking over large areas which we could cover with solar panels for mainly energy production and also shading. In our case, the solar carpet is designed to supply electric cars as it is linked to charging stations and it is not connected to the grid. Looking at the methodology and results section, the methodology is based on the following process of 7 steps, which start by determining the daily energy demand of 65 kilowatt-hour per day for 3 electric cars, each of battery capacity is 22 kilowatt. As the daily AC load is high, the system voltage is then 48. The number of solar panels is calculated with the first equation, and it is 102 panels that will be mounted on the steel structure of the carpet with a power of 64.44 kilowatt. The number of panels connected in series and in parallel is 2 and 51 respectively. According to the software SAM, the energy produced during the first year is 42,150 kilowatt-hour, that is degraded by 0.5% every year. The capacity of the battery is determined from the first equation and it is 7,966. Therefore, the whole system requires 40 batteries. For wiring, we need in series 4 batteries and in parallel 10 according to the equations 3 and 4. The inverter should be sized to provide 125% of the maximum load we wish to run simultaneously at any moment. The selected inverter has a power of 25 kilowatt, therefore we need 4 inverters. The charge controller must have a specific current and voltage determined with the first 2 equations on the slide. Also, we must account for the minimum input current determined in the third equation. Based on the fourth equation, we need 17 charge controllers. A crucial element in our system is to assure proper wiring between the components. So we have 3 different wires in the system, and their cross-section area is calculated with the equation shown on the screen. Therefore, the copper wires should be of 120, 325 mm square between the PV arrays and the batteries, between the batteries and the inverters, between the inverters and the AC load respectively. It is critical to protect the components of the system when the maximum load current is connected through installing fuses and switches. The voltage and current is calculated based on the equations shown on the slide. Performing an economic analysis is necessary to identify if the system is potential from an economic perspective or not. The capital investment is described by the table and it is 661,000 Moroccan dirham. The life cycle cost is used to estimate the total cost of owning and operating the system over its useful lifetime, and it is expressed with the first equation. The lifetime of the PV array is 25 years, and of the batteries is only 5 years. Therefore, we need 4 extra groups of batteries, and their present worth is calculated with the second equation. The inverter lifetime is 10 years, therefore an extra 2 groups of inverters should be purchased, and their present worth is calculated with the third equation. We also have to account for the present worth of the operation and maintenance as expressed in the fourth equation. Summing all the costs, the LCC is about 1,460,000 Moroccan dirham. The levelized cost of energy identifies how much money must be paid per unit of electricity to recoup the lifetime costs of the system, and it is calculated with the equation shown on the slide. The following table is an explicative table of how the calculations are made, from which the LCOE is 1.6 Moroccan dirham per kilowatt hour. The payback period is an important indicator for the economic potentials of the system. As explained in the table, the payback is estimated to be 10.5 years. Finally, it is interesting to account for how much the designed PV carport mitigates emissions. This amount is determined by the equation shown on the slide, and it is estimated to be 657,357 kilograms. To conclude, the solar carpet PV system plays an important role in the domain of sustainability in transportation, as it provides shading for the cars and contributes to clean energy production. Most importantly, the analysis made and the obtained results for the designed system can further be applied in applications for solar PV system sizing. And this is the list of the references used. And thank you.